All right, in 4.2, we are going to take a look at logarithms, okay, or logarithmic functions. So to start, let's think about this exponential function and try to find its inverse. Okay, so we talked about finding inverses a couple of chapters ago. To do that, the first step is to switch all x's and y's and then try to solve the new equation for y. So if I switch my x's and y's, I'll have x equals 2 to the y power. Now, I need some way to undo y, right? This exponent. I need some way to bring that down, to undo a power. From what we've studied so far, we don't really have a way to do that, which is why we are going to introduce this idea of logarithms. Okay? A logarithm is an inverse of an exponential. So what I'm going to do is take the log of both sides here. And we're going to talk a lot more about solving equations here in the next section, but I'm essentially going to take the log base 2 of both sides. I'm not multiplying, right? I'm taking the log base 2 of both sides of the equation. What I'm left with then is log base 2 of x on this side, and then over here, raising a power or having a base of 2 to something and a log of base 2 cancels out. I know that that doesn't make a whole lot of sense right now, okay, but we're going to take a look at what that means here. Just understand right now that a logarithm is an inverse of an exponential. Logs and exponentials undo each other. Okay, so what we're really going to focus on today is going back and forth between log form and exponential form. Okay, so in this first section, we are given some exponentials and we want to turn them into logs. Logarithmic form looks like this, right? Y equals log base a of x. So what I'm going to do to change something like this into logarithmic form, the base of the exponential is going to become the base of the logarithm. Okay? So the base in this case is 4. Right? So to rewrite this, I'm going to start by writing it as log base 4. Right? And it looks like a subscript. Right? We write that down here. So log base 4 of 64 equals whatever the exponent is. In this case, that's 3. So the way that I learned it in school was just bases are bases, right? The base of the exponential and the base of the log remain the same. And then logs are equal to exponents. So bases are bases, logs are equal to exponents. Another method that you may have seen before is this lazy 7 thing, to go back and forth between an exponential form and logarithmic form. So the lazy 7 idea says, well, you start with the base, right? So log base 4 of 64 equals 3, right? It kind of looks like a 7 laying on its side if you connect them like that. So log base 4 of 64 equals 3. Right? And again, this logarithm idea is just an inverse of an exponential. It's so that we can undo an exponential. And again, we'll take a look at solving problems like that in the next section. For now, we just want to focus on being able to go back and forth between log form and exponential form. Okay? So same idea for this one. Right? We would say log base 2/3 of 4/9 equals 2. Okay, and that would just mean 2/3 to the second power equals 4/9. Same thing, right? Lazy 7. So now we can say log base a, bases are bases, of 7 equals -2. For this one, log base c, I'm sorry, that is not correct. The base of this exponential is b. So I actually wanted to point this out here, that in order to think about this lazy 7 idea, we would need the exponential portion on the left side, right, to make it look like this lazy 7. So this would be log base capital B of C equals D, right? Lazy 7 like that. Now, for this last example, in order to use our lazy 7 or to rewrite as a log, we need to get the exponential by itself first. So I would need to add the 1 over, divide by 3, and then I can rewrite this as a log, okay? But we need to get the exponential by itself first. So now I can say log base A of 11 thirds equals 2. All right, so now let's take a look at going the other way. All right, let's say we're given logs and we want to write them in exponential form. Okay, well, we're actually going to do something very similar. So we're saying the base of the log is going to be the base of the exponential. And then we can actually think about doing a lazy 7 here as well. So this would mean 3 to the 5th power equals 243. Okay, bases are bases, logs are equal to exponents. Here, we can write this as 2 to the x power equals 5. Right? Now this one is backwards, right? If we're thinking about the lazy 7, we can always rewrite it as log base 7 of 1 over 49 equals -2. So that would mean 7 to the -2nd power equals 1 over 49. Okay, and these are true statements, by the way. Make sure that we're understanding our rules of exponents here. Right? 7 to the -2nd power would mean 1 over 7 to the 2nd power, and 7 to the 2nd power is 49. Then we can do the same thing with variables, right? So this would mean a to the b power equals c. And then finally, just like in our final example for an exponential, here we need to get the log by itself. Okay, so as of now, I am multiplying by 3 out in front. So I need to divide both sides by 3 to get log base 27 of 3 equals 1/3. Now, note that we cannot do anything to the value on the inside of the log, right? This is on the inside. If I'm dividing both sides by 3, that value is not going to change. Okay, the only thing that's going to change is anything on the outside of the log, right? If I'm dividing both sides by 3. So now, to rewrite this as an exponential, we're going to say 27 to the 1/3 power equals 3. Okay, and again, remember our rules of exponents. This 1/3 power is actually the same as the cubed root. So this would be like saying the cubed root of 27 is equal to 3, and that is a true statement. Okay, so now let's try to evaluate some logarithms and really think about what this means. Okay, so what we're saying here is 5. I'm gonna rewrite this as an exponential. Okay, 5 to what power, right? That's what's going to go over here. The exponent is what's over here, equals 25. Well, 5 to the 2nd power equals 25. So Log base 5 of 25 is equal to 2 because 5 to the second power equals 25. Okay, so that's what we're thinking about when we're evaluating a log. All right, so how about this one? 7 to what power equals 7? Right? 7, well, this should be an easy one. 7 to the first power equals 7, right? Oops. So anything to the first power equals itself. How about this one? This one might be a little bit trickier to think about. 1/3 to what power equals 9? Well, here, again, we need to think about our rules of exponents. I essentially want to bring this 3 to the numerator somehow and, and then square it. Well, what I can do is raise that to the negative second power, right? So if I've got 1/3 raised to the negative second power, well, that would be like 1 to the negative second over 3 to the negative second. And we talked about if we have negative exponents, if they're in the denominator, bring them to the numerator and make the exponent positive, or if they're in the numerator, bring them to the denominator and make the exponent positive. Okay, so this would end up being 9 over 1. So 1/3 to the negative second power is equal to 9. For this last one, again, we're thinking 4 to what power equals 1/2? All right, well, here, this one is a little bit, again, weird to think about. I essentially want to bring this 4 to the denominator, but then take its square root. Right? I'm decreasing in value, and it just so happens that 2 is the square root of 4. Well, so I know that my exponent's going to be negative if I'm going to have to bring that to the denominator. And again, thinking back to when we studied exponents in Algebra 2, 4 to the negative 1/2 is actually going to be 1/2 because what this would be, okay, 4 to the negative 1/2 would be the same as 1 over 4 to the positive 1/2. And then a 1/2 power is the same as a square root. So this would be 1 over the square root of 4, which would be 2. So 4 to the negative 1/2 power is equal to 1/2. Okay, so that's what it means to evaluate logarithms. So let's look at a few properties of logs, right? These apply to all logs. And we looked at this example already, right? When we said log base 7 of 7. It doesn't matter what number we put there as long as it's the same. Log base a of a will always equal 1 because a to the first power equals 1, right? And we can rewrite that idea as an exponential. Similar idea here. We're thinking a to what power equals 1, right? Well, anything to the 0 power equals 1. So here we can say log base a of 0 equals 1. Now, a couple other properties that won't really be able to explain why these are true until we look at the next section, okay? But log base a of a to the x power is just going to equal x. And then a to the log base a of x is also just going to equal x. So these are going to be ways that we can get x, right? If we have some variable by itself. Again, I'll explain why these work in the next section. But for now, just understand that these are properties that will always be true. Log base 7 of 7 to the x will equal x. Log base 43 of 43 to the x will equal x. All right. So now let's take a look at common logs and natural logs. All right. A common log is just a log with a base of 10. And when we write out these, we just don't include the base. So if you ever see a log that doesn't include a base, that's just base 10. We'll look at a few examples here in a second. Okay. Natural log is a log with a base of e. Okay, and we looked at the number e in the last section, right? 2.718281828459045, right? And it's an irrational number. Now, the notation for a natural log is ln. And a lot of times you'll see it written in script or cursive. It's, I believe they use the French log natural. That's why it's ln instead of nl, right? But it's ln stands for the natural log, and this is just log base e. All right, so let's look at, well, first, let me mention that these are so important. They each have their own button on your calculator, right? This log button here is log base 10, and then this button here, ln, is the natural log, log base e. So let's look at a few examples here, okay? This log of 10, well, what this really means, if we don't see a base, that means log base 10 of 10. So log base 10 of 10 means 10 to what power equals 10? Well, that's just 1. Here, ln of e, natural log of e, what that means is log base e of e. Again, same reasoning. E to the first power will equal e. Here, again, if we don't see a base, that means log base 10. So this is log base 10 of 1. So 10 to what power equals 1? Right? Well, here, if we're thinking anything to the 0 power equals 1. So 10 to the 0 power equals 1. Same thing here. ln of 1 is log base e. So log base e of 1. Well, again, anything, e is a number, right? So e to the 0 power will equal 1. And then here, these are those other two properties that we just looked at, right? If I have the same base, okay, and the same value here, log base 10 of 10 to the x is just going to equal whatever the exponent is. Same thing here. This is log base e of e to the x. So that's just going to equal x. And then same logic here. 10 to the log base 10 of x will equal x. And e to the log base e of x will equal x. Okay? Now, remember, these statements are true as long as this value and this value are the same. Right? It doesn't have to just be e and 10. It could be anything. Okay? So let's evaluate some of these logs then. Okay? So here, 10 to the log of 22, again, if we don't see a base, that means log base 10 of 22. So since I have the base of my exponential and the base of the log are the same, those essentially cancel out, and that just equals 22. Here, again, natural log really means log base e. So this is log base e of e to the 5th power. Again, if the log and the exponential have the same base, they cancel out. And this would just be equal to 5. This last one, similar idea. So we'll have log base e of 1 over e to the 2.5 power. So here we have to think a little bit and rewrite this. So e to the 2.5 power in the denominator would be the same as bringing that to the numerator and making the exponent negative. Right? I can do that. Right? I don't have to just change negative exponents to positive exponents. I can go the other way. And if I have a positive exponent in the denominator, I can bring that to the numerator and make the exponent negative. So now it's a lot easier to see that this follows this same pattern. We get base of the log is the same as the base of the exponential. So this would just be equal to negative 2.5, the exponent. All right. In these next three, right? We have a different bases and different values. So on this first one, we've got a log inside of a log inside of a log. We want to start at the innermost value and work our way out. So here, log base 2 of 8. Okay, I just want to focus on that. So this part is saying 2 to what power equals 8? Well, 2 to the third power would equal 8. So just this portion here, log base 2 of 8 is equal to 3. So I can rewrite this as log base 4 of log base 3 of 3. Right? I just replaced log base 2 of 8 with what I know that to be, 3. Now I can work on the next log. So log base 3 of 3. Well, that's just going to be equal to 1 because 3 to the first power equals 1. So now I'm just going to replace this part with what I know it to be equal to, which is 1. So now this is going to be log base 4 of 1. And now finally, log base 4 of 1. Well, 4 to what power equals 1? Anything to the 0 power equals 1. So this whole thing was just equal to 0. Right? In these next two examples, we've got some square roots. Right? On these, we want to think about rewriting them as a power. So let me just take 2 to the square root of 2 and kind of think about rewriting this. Now, for problems like this, there isn't going to be an exact way to do these. We just kind of have to think about manipulating the square roots to get them to make sense. Okay, so we're just going to walk through a couple examples here. On this first one, 2 times the square root of 2. Well, I can rewrite that as the square root of 4 times the square root of 2. Okay, it might not be immediately obvious why we would rewrite 2 as the square root of 4, but if I do that, then I can multiply those together. The square root of 4 would, and the square root of 2 would multiply to the square root of 8. So I can actually just rewrite this as log base square root of 8 of 8. So now we want to think about the square root of 8 to what power equals 8. Well, if I take the square root of 8 and square it, that would equal 8. So rewriting this helps us see what these values would be. Right? We want to do something similar here. Right? We don't have to rewrite the base, but we want to think the square root of 3 to what power is going to be equal to 27. Well, I know that 3 to the third power is equal to 27. But here I need to take the square root of 3. So what I actually have to do, the square root of 3 squared would just be equal to 3, right? But then I want to take that and cube it. So here, remember, whenever we have a power to a power, we multiply those together. So the square root of 3 to the 6th power would equal 27. Okay, so that's the thought process that we want to go through here. All right, so the next set of problems are something similar. There are just x's in them. So we want to go through the same thought process, right, to work through these problems. So to do these, okay, we want to think about potentially rewriting them. The first two, we don't really need to rewrite because the log is already by itself. We just need to think, well, 3 to what power equals 9? Well, 3 to the second power equals 9. So x would be 2. For this one, I want to think 4 to what power equals 1/4. Well, this one might not be as immediately obvious, but we want to think, well, I want to get this 4 to the denominator and leave it alone, right? Well, to do that, we would want an exponent of 1 in the denominator. So to bring it to the denominator, I would need an exponent of -1. That means in this case, x would equal -1. Something like this, where x is inside of the log, it's really going to make sense to rewrite this as an exponential. So we're going to say 2 to the third power equals x, and 2 to the third power is just 8. In our next few examples, here again we want to go through that same process. 3 to the -4th power equals x. And just rewriting this using that lazy 7 idea. So this would be 1 over 3 to the 4th power, and 3 to the 4th power would be 81. So x would be 1 over 81. For this next one, again, we want to think 2 to what power equals 2 times the square root of 2. Now, again, we want to think this would be the same as the square root of 8. Okay, we already went through the process of thinking about why that would be the square root of 8 in that previous example. So I think it's going to be a little bit easier to rewrite this. Okay, so 2 to what power equals the square root of 8? Well, I know 2 to the third power equals 8. So let me think about that here. So 2 to the third power equals 8. But I want the square root of 8, right? That is the same as the 1/2 power, right? I want 8 to the 1/2 power. So what I can do is from this equation, I can actually raise both sides to the 1/2 power. That would get me to the square root of 8. So here, if I'm raising a power to a power, I'm multiplying. What that means is 2 to the 3/2 power is going to be equal to 8 to the 1/2 power, or that's the same as the square root of 8. Okay, so that's kind of the thought process that we want to go through here. So that means our answer, x, is equal to 3/2. Right? In the final example here, we definitely want to rewrite this as an exponential. This would be 3 to the 0 power equals x squared minus x minus 5. 3 to the 0 power, right? Anything to the 0 power is just 1. So now we just have an exponential to solve. To do that, I want to get everything on one side equal to 0. So I'll subtract this 1 over. We'll get x squared minus x minus 6. And now we want to factor. So two numbers that multiply to -6 that add to -1. That looks like that would be -3 and +2. So this would factor into x minus 3 and x plus 2, which means I would get x equals 3 and x equals -2. Now, whenever we're solving a problem like this, we do need to test that each of these work. We need to test for extraneous solutions. So if I plug 3 in, right, I will have 9 minus 3 is 6, minus 5 is 1. So that works. 3 to the 0 power equals 1. If I plug -2 in, -2 squared would be +4, minus a -2 would be +2, so that would be 6, minus 5 is 1. 3 to the 0 power equals 1. So both of those do work. Right? The final thing that we want to look at in this video is the domain of a log. So we already mentioned that an exponential and a log are inverses. So we know that from the last lecture, the domain of an exponential is -infinity to infinity, and the range is 0 to infinity. The inverse then would have those flipped. So a log is going to have a domain of 0 to infinity and a range of -infinity to infinity. So And again, that's without shifts, right? We could have shifts. What that means for actually finding the domain is that whatever is on the inside of a log has to be greater than 0. So we've looked at a couple of things that could restrict the domain before, right? Whatever was on the inside of a radical had to be greater than or equal to 0. And we could not have 0 in the denominator of a fraction. We're going to introduce a third one saying that whatever is on the inside of a log has to be positive. So whenever we see a log, all I'm going to do to find the domain is say that whatever's on the inside has to be greater than 0. To solve this, I can add the x over, and I'll get 3 is greater than x, or I could rewrite that and say x is less than 3. So we want to rewrite our domain always in interval notation. So here, x is less than 3 means I want negative infinity all the way up to 3. So to find the domain of a log, we are just saying whatever is on the inside has to be greater than 0. In this example, we have 2 logs being added together. What I want to do here is separately find the domains of each piece. Okay? I guess this should probably be a number here instead of a variable. So let's say here, x plus 2 is going to have to be greater than 0, and here, 3x plus 1 is going to have to be greater than 0. Here, subtract the 2 over, we'll get x has to be greater than negative 2. Here, subtract the 1 and divide by 3, we'll get x has to be greater than negative 1/3. So what we want to do with these 2 pieces of information is find the intersection. So we've talked about this idea a little bit before, right? If here I'm saying I want everything greater than negative 2, and here I'm saying I want everything greater than negative 1/3. The intersection means where these 2 graphs or these 2 number lines intersect. So they would intersect on this portion, right? Everything greater than negative 1/3. Since this little piece here from negative 2 up to negative 1/3 isn't part of both graphs, I would not include that. So the domain here is going to be negative 1/3 to infinity. All right. One final example right here. Again, we just want to take whatever's on the inside and say that that has to be greater than 0. So this, we actually have to think about what we did in the last chapter. Right? Whenever we have a rational function as an inequality, we want to use our test points, right, and make a sign chart. So to do that, we said, well, anything that makes the numerator equal to 0 and anything that makes the denominator equal to 0 are going to be values on my sign chart. So if I set the numerator equal to 0, well, that's going to get me negative 1. And if I set the denominator equal to 0, that's going to get me positive 3. So those are the 2 values that are going to go on my sign chart. And then I'm just going to take a test point. So take something less than negative 1, say negative 2. So if I plug that in, negative 2 plus 1 would be negative. Negative 2 minus 3 is a negative. A negative divided by a negative is a positive. From negative 1 to 3, let's test 0. 0 plus 1 is positive. 0 minus 3 is negative. So a positive over a negative is negative. And then take a value bigger than 3, say 4. So 4 plus 1 is positive. 4 minus 3 is positive. Those will be positives. So my domain here is anything that makes this greater than 0, any values that are positive. So my intervals then would be negative infinity up to negative 1, not negative 1 to 3 because that interval is negative, and then 3 to infinity. All right. So that is it for this video. The final question is going to pop up asking you what questions you have.